Hello, welcome everyone. Thanks for joining us at today's webinar, What's New in ENVI Deep Learning 2.1. My name is Bill Okubo. I'm one of the product management team here, and I'm excited to be joined by Zach Norman. He's another one of the product managers. Zach is going to provide all the new latest and greatest functionality of ENVI Deep Learning 2.1. It'll take about 40 minutes. There's a couple of quick housekeeping items before we get started. All attendees are muted, so if you have any questions at any point, go ahead and type in the chat box in your control panel there. And then at the end of the webinar, we'll record this and we will provide the slides to you in the next few days. All right, so that's it for housekeeping. Let's go ahead and turn it over to Zach. Zach, please get us into the webinar.
All right, thank you for the introduction, Bill. Let's go ahead and have a look at what we're going to be talking about today. So we're going to go through a brief introduction to give a little bit of background and context for ENVI Deep Learning and machine learning, and then we will walk through the features for each product and wrap up with some little nice to haves at the end before opening it up for questions and discussion. So with that, let's get started. So here's quick little contact information for Bill and myself. There's our email addresses. We'll try to answer as many questions as we can at the end, but if we don't get to yours, feel free to send us an email and we'll do our best to get back to you. So with that, let's go ahead and get started because we got a lot of good stuff to cover today. So first, the background we want to provide is a little bit for the ENVI Deep Learning module. This is something that's been around for, I want to say, 4 or 5 years now, and adds a deep learning workflow to ENVI built around being able to create training data, create models, see how they perform, rinse and repeat. And our focus is really built around not forcing you to program so that you can click buttons. You don't need to be an expert at Python or deep learning and hyperparameters or even have to know what those are in order to use the tool sets. You can see some of the features on the right here that you can use the deep learning module for. We're not going to go into all those details here, but you can check out some of our other webinars and presentations for more information. And the second part of our little intro here is ENVI Machine Learning. So this is much more recent. This was last fall, I want to say, was when we had our release and a standalone webinar for machine learning in ENVI and IDL. But it's the exact same workflow. You can create training data, generate your machine learning models, see how they perform, rinse and repeat. The main difference here is that with machine learning, it takes minutes instead of hours to sit down, label some features, use that spectral information to go through and find similar pixels within your scenes. So we're not going to go through all the details of capabilities. Feel free to read the slides. You'll get a copy of them and check out our website for more details. But the one other piece of information we want to make sure to cover today is talk a little bit about the differences between machine learning and deep learning, mostly for access. So machine learning is free and doesn't have any cost associated with it. It is packaged as part of the deep learning module. However, everyone should have access to the deep learning module through our downloads portal. So you can sign into your account, go view products. You should see ENVI Deep Learning right there. You can download that, install it today, and have access to machine learning. You do not need a license of deep learning in order to use it. Deep learning, however, is a separate module that you need to purchase through ENVI. The big difference between the two, machine learning uses the CPU, deep learning uses the GPU, and does require an NVIDIA GPU in order to use the tools. So that's all I'm going to say there. Like I said, if you want to learn a little bit more, check out our website. We have some other videos that talk about some of the differences, use cases, and we have several webinars covering each. So with that, let's pivot and dig into our content for deep learning. First, we're going to go through some of our changes that we've made to TensorBoard. And to give a little bit of background information here, TensorBoard is a web application that will launch when you're training models through ENVI Deep Learning, which gives you a way to interact with and visualize the performance of your model, i.e. accuracy, precision, recall, loss, things like that. TensorBoard also allows you to look at previous training sessions, overlay metrics on top of one another to see if changing label data or maybe tweaking the couple of parameters you have access to makes a difference or not with what gets reported during training. On the right, you'll see a screenshot of the new TensorBoard user interface with some of the metrics that get reported, which we'll talk about here in just a second. So with that, first thing I want to show is a screenshot of our old version of TensorBoard. And this is something that's been in the product for quite a while. And at a high level, is very basic. It didn't really give you the ability to view all the metrics side by side. They were split up by batch, epic for training and validation. Whereas it would really be a lot better if you could view everything all on the same graph all at once and have more insights into the performance of your models. So with that, here's a short little video that covers at a high level most of the features. Now we're going to dig into each of these here in just a second, but as this video goes through, the first thing you should hopefully notice is that you have per class metrics that get reported for precision, accuracy, and recall. We also have confusion matrices and some really cool visualizations so you can see how performance changes over time during training. Like I said, we'll talk about this more here in just a second, but this new TensorBoard user interface allows you to look at everything on the same graph for batch, training, and validation. But anyways, we'll get to that in a second. So here's a list of the changes that have been made as part of the TensorBoard update. I'm not going to go into detail for everything here, just an effort of time, but probably two of the big changes that we have is that the x-axis for any metrics that reported represents the number of samples that we have trained so far. So if you have different batch sizes with different size GPUs, you can still compare training sessions from one to the other. The other component of this is that we have three separate logs that get generated. We have batch, training, and validation. And the nice thing is that batch, training, and validation all report mostly the same logs, and you can view them all on the same graph at the same time. Let's go ahead and take a look at what some of the metrics actually look like. First, we have our overall metrics. These are indicators of the general performance of your model and summarize the overall behavior rather than more specific information like per class, precision, accuracy, and recall. We'll get to that in just a second. Here we have accuracy, precision, recall, and loss. You want accuracy, precision, and recall to be increasing as you train and loss to be decreasing. You have a screenshot on the right showing the accuracy metric with our batch, train, and validation logs all displayed. And if I bring up my little animation here, you'll see that box outlines the same point on the graph. So as you move your mouse through the graph, it highlights the closest point, and then you have the little legend which shows up at the bottom of the image there to give you the actual value of the metric at that step or point in time. One of the changes with our overall metrics is that we now have several different types of accuracy that are being reported. We have our traditional value as shown on the left. We then take an average of the accuracy by each class and represent that. Then on the right, we have two different types of accuracy that are focused exclusively on foreground. Terminology here. Foreground represents pixels or features that you're interested in compared to the background, which is everything else. The two metrics on the right are the same as the two metrics on the left, except they exclude the usually large class of background pixels to help make sure that you get a better idea of how your classes are performing. This is something that helps a lot when you have rare or small features or the number of background samples compared to foreground is quite large, meaning there's a lot more background than the things that you're interested in. All right, let's take a look at some of the specific per class metrics that we generate now. So as was shown in the very quick video at the beginning, we have accuracy, precision, and recall that each get reported. These metrics for a class-by-class basis are reported only at the end of training, not during each step. So you'll have to practice a little bit of patience to see what these look like, and wait 10, 15, 20 minutes and see how they kind of evolve over the course of a few steps of training. If you don't have much training data or you have rare features, one thing that's really important to note is that these values might jump around. That's because during training, we have some random selections for the portions of the image that we actually train on. So it's going to be a little bit different every time you go through training data for each epoch. So just keep that in mind. You'll see the same thing with confusion matrices as well, which we'll talk about more here in just a second. But we've got one more slide here just showcasing a multi-class example where we have 4 classes. This is straight from the tornado damage detection tutorial that's packaged as part of deep learning, just to give you another look at what these might look like. For this example, I've also taken some screenshots showing our training and validation metrics being displayed in the exact same graph. And top to bottom, you can see accuracy, precision, and recall for each. So I'm not going to spend too much time on this. I just wanted to make sure to include this so there's a little bit more of an example of what this looks like with a real training session. One of the things that's important to note here is that these metrics all actually come from a confusion matrix behind the scenes. This is the real exciting information that I like to look at and visualize, at least during training, which brings us to confusion matrices. So this is a little animation that I tried my best to try to get the left side and right side synced up as you went through, but it's just showing what the visualization user experience is like when you're looking at confusion matrices. After 15, 20, 30, 50, however many epochs of training, you have a nice little slider that you can move, and you should hopefully see progression going along the diagonal of the confusion matrix. Like I mentioned a couple slides ago, this is going to vary a little bit depending on how much training data you have and how rare your features are, because we have some random selection during the training process. So that goes for validation data as well. We take some random samples from training and validation, which means that these can jump around a little bit. So going back to one of the earlier slides with TensorBoard, you want to make sure that those overall metrics, accuracy, precision, and recall, are trending upwards, and loss is trending downwards as you go. This is something that we'll be investigating a little bit as we move forward to see how we can help make this a little bit more stable and not jump around as much. But for an example like this, which is straight from our tutorial, our documentation for tornado damage detection, where we have a pretty good class balance, it works very well. All right, we have, I think, 1 or 2 more slides to talk about for metrics, and then we're going to pivot to some other features. One of the last things, and this is also a new addition to TensorBoard reporting here, is distributions and histograms. Distributions are shown on the left, histograms are shown on the right. Distributions and histograms represent similar values. Distributions show it in a horizontal 2-dimensional plot where you have the minimum value for a metric. So in this case, it's accuracy by each class. And then you have an upper value. So it shows you basically the range of accuracy at each epoch of training for a specific metric. Ideally, as you're going along, you want your minimum and your maximum to approach each other and both approach a value of 1. The difference between distributions and histograms is this kind of cool 3D view where you can move your mouse through the plot over time, and it will highlight the minimum value for a metric, the maximum, and potentially some other ranges in between. So it's an actual histogram that you'll see. So it gives you the range, just like you see on the left, but also some information about kind of relative count or intensity for those as well. Just to illustrate that these are similar metrics, I made some fancy little lines here to try to show the lower curve for our distribution on the left and the lower curve for the histogram on the right. And then we can do the same for the upper curve. The upper curve is a little bit harder for us to see because it's kind of blocked a little bit, but hopefully that illustration comes across for how these two metrics that get reported are similar. All right, we're going to pivot a little bit from here to talk about something, well, it's more metrics adjacent than anything else. But I want to make sure to spend just a minute talking about, what you see in TensorBoard versus real world performance of your model. Performance meaning, how well is your model able to identify features in new data that you didn't train on. Like I've said a few times, your metrics might jump around a little bit, depending on if you have rare features, because we have some randomness in training. And with that in mind, don't fret if you do see metrics that look a little low, especially for precision, accuracy, and recall for different classes. Sometimes low performance can actually be because you, as a labeler and person using deep learning, might have had two classes of features that are very similar to each other and confusing, which means that artificially your performance of your model is going to be worse because it can't differentiate between two of your classes, for example. So one of the things I always recommend is that it's important to just get an image, get your model, process it, and look and see what the results actually look like, and you might be surprised. So that's always probably the best test, I think, of performance is taking some random data sets, processing them with deep learning, and inspecting them. Go through, look at histograms and all the places where there might be spurious pixels or false positives or things like that to get a real bearing of how well your models are working. So the only other thing I'll add here is that when you are processing imagery and you're generating classification images, that's not always the last step in your workflow. We have plenty of other tools from traditional remote sensing, algorithms and processes to help you clean up and remove false positives. So for raster-based processing, I've got a list on the left, and vector-based, I have a list on the right. Raster would be something you'd use with pixel segmentation. Vector is most likely something you'd use with object detection, or if you convert your classification images from pixel segmentation into vectors, then the right would apply as well. So just keep in mind, there's a lot more than just deep learning when it comes to processing imagery. Post-processing is a key and really important step of any image processing workflow. So here's some of the tools. Sit down, play with them, try them out a little bit. All right, so that wraps up our conversation about TensorBoard and metrics. Let's pivot a little bit to talk about our next major feature, which is a new architecture that's been added for pixel segmentation. For this release of deep learning, we now have two models that you can choose from. For segmentation, we have SegUnet++ and SegUnet. SegUnet++ is the new architecture, and it's the default when creating a new model. We'll show some examples here in just a minute talking about some of the differences, but there's a few things that I want to call out before we get to our nice little screenshots. After a little bit of investigation, this was something that we decided to make the default because we noticed that when you have smaller training sessions where you might have 50 or 100 examples of a feature and you might be training for 15 or 20 minutes, that the SegUnet++ model performs better. So in general, you might see less noise and fewer, kind of standalone detections that are just like single pixels here and there. We'll talk about that in just a second as well. The network size is also a little bit smaller and about 10% faster. So with training sessions that take an hour, that's only, 5 or 6 minutes that it might save you, but every minute counts, especially if you're an impatient person like myself. So on the right here, you'll see the initialized pixel segmentation model tool with the architecture drop down as well, which, like I said, defaults to SegUnet++. So before we go through the next slides, I want to add a little bit of a caveat. We're going to be showing some screenshots of model performance that frankly aren't the best. And that's because we're using a very little amount of training data, and we're not trying to sugarcoat things and say, oh, ENVI Deep Learning's perfect all the time. Because it's not. That's not the case. There's a lot of factors that come into play when creating new models, and starting with a proof of concept model with small amount of training data and very little training is a great way to get started to make sure that you can detect a feature you're interested in. With that, here's our first example, which shows a comparison between the SegUnit model on the left and the SegUnit++ model on the right. I'm going to pause here for a second because at a very high level, you should immediately see a difference. The image on the right shows dramatically fewer false positives, where on the left, with very little training, we have water that just kind of gets detected. So this is a very basic model looking for ships in about, I think it's 1 meter, 2 meter imagery. It might be half meter, but this was NAPE data over the US. So as I mentioned, we're not trying to show perfect results here. We're trying to show how with very little training, you have natively better performance with this new architecture. So this little video just kind of goes through, zooms in a little bit, gives you a little bit more of a sneak preview. Like I mentioned already, the answer is that the image on the right is working better. So here we have another video, and I'm going to skip forward just a little bit, or I'll wait to pause actually. We'll pause right here. So we have our original image on the left, where you can see some boats. It's a little bit lower resolution because the boats kind of clump together a bit. In the middle here, we have our SegNet++ architecture, and on the right, we have our old, well, not necessarily old, but our current model of SegUnit++. There's just the original SegUnit. You can notice a dramatic difference between the SegUnit++ and SegUnit model on the right. SegUnit is much better at only detecting ships, whereas SegUnit just kind of grabs a little bit of everything. It's not nearly as, accurate or precise. And we can let this go for another second here, and there's some other examples that this will show at the end. We'll pause right here as well. We have the same style where we have some docks with ships attached to them, and we have our model in the middle of the SegUnit++, which gets a little bit of the dock as well, but also just gets the ships. And then all the way on the right, we get just this kind of giant blob, which isn't quite correct. So that's our first example here. Next, we're going to go through and show some examples from the tornado damage detection tutorial, just to give you a comparison kind of side by side. So here for this first screenshot, we have our SegUnit++ model on the left, our actual imagery in the middle, and our current model, the SegUnit, on the right. One of the comments I made earlier was that the new model doesn't detect as many spurious pixels. If you look at some of the results in the top right of this slide, you'll see little gaps here and there. You'll see kind of random thin strips of pixels, versus over on the left, we have a much better job of just kind of general clumping or more consistent shapes of pixels rather than just these random, here and there we have, flip-flop between the red and the orange, which is rubble and structural damage. So the SegUnit++ model does a much better job at reducing kind of noise natively, is how I would describe it. Here's another screenshot showing some of the differences between the two models. In general, the SegUnit++ is also a little bit better at determining the correct class. And this is an example where it's a great teaching lesson, but we have two classes that look very similar to one another. It's roof damage and structural damage. Those get confused sometimes. So here, right by our text on the right, you'll see that we have something that gets reported as structural damage, which it's kind of hard to tell, but it almost looks more like it's just damage to the roof. We're not seeing kind of in through the house. So in general, the SegUnit model kind of lines up a little bit more with what we would expect to see for our results here. Here we have another example. This is for crosswalks, and there's no crosswalks in this image at all. And I picked this spot on purpose because I just wanted to show some places where, in general, when you have very little training data, for this crosswalks demo here, we had maybe 10 data sets, and there might have been 50 crosswalks in them, so not much at all. Here on the left, we have our SegUnet++, where if you can see my cursor, we actually have some false green pixels that you'll see on some cars. But over on the right, we have a whole bunch of purple pixels that represent, outlined crosswalks, but that's not really what those are. So here we have some other examples showing the SegUnet++ model on the left, having a much better ability to actually detect and outline crosswalks compared to our SegUnet model on the right. Again, this is with a very small training set and with about 15 minutes of training. So we're not trying to make a perfect model, just trying to illustrate some of the differences between the two. Here we have another example where on the left, SegUnet++ is able to detect crosswalks much better at this intersection, if you look where my cursor is. On the right, the SegUnet model has a hard time. Both of these models, interestingly enough, have some false positives around some of these white cars. I'm not too surprised by that because we have white cars with black windows, looks like maybe some sunroofs, maybe they're Teslas, I don't know. But it's kind of the same style of pattern as what you might see on a crosswalk with something bright white and then with the dark asphalt behind it. And anyways, scooting on a little bit more, here we have more of the same. I'm going to skip through this slide just so we can keep moving on. So this last example, we're going to show a couple of aircraft detections. This is one where we actually had a fair amount of training data. We had about 40 images, and I want to say it was 1,500-ish examples of 4 classes of aircraft. And the point of showing these is that they're effectively the same. So our models for SegUnet++ and SegUnet do a very good job at detecting aircraft when they've gone through quite a bit of training with 40 images, and I think it was about 8 hours, if I remember right, when I had generated these models. So here's another example. This one, I forgot the legend on the last one, but here we have the Tu-95 Bear, and we have nice green circles in the center of each on the left and the right. If you are looking closely, just like I mentioned for the tornado damage example, the pixels for SegUnet++ are a little bit more circular and kind of a blob, versus for SegUnet on the right, you'll have some holes and some gaps here and there, which you need to use some kind of post-processing before you turn that into a vector so you don't have more than one, air quotes, detection as a vector. And then here we've just got another example showing some kind of random aircraft. This is one where the SegUnet model did a little bit better. It's also kind of hard to see because some of the clumps of pixels are really tiny on the left, but we have some blue clumps in the right. Let me show with my mouse here, where we have some helicopters scattered in amongst these other just kind of miscellaneous aircraft. And we can also see those on the left, but they're much smaller, a little bit less pronounced. So with that wraps up our deep learning features. Next, we're going to pivot a little bit to talk about machine learning. All right, moving on to machine learning. Oh, never mind, I lied. I forgot we had one more slide here. So one of the things I want to make sure to call out is that with this release of deep learning, we did introduce a breaking change. For the longest time, we had a model called single class, and that was not a concept that really fit with the newer paradigms of how to use and create deep learning models within ENVI. So this old concept we've stripped out. So it was a good opportunity because we're adding a new model with that SegUnet++. And so you can no longer create these old single class models. However, you can still use those models to process imagery. So your model, if you have an old one sitting around, is not just defunct and useless. You can still process data with it. You just can't improve the training or generate a new one. So please keep that in mind, but I think everybody should be using the new SeguNet or SeguNet++ models anyways, so that probably only impacts a handful of users. So now we're going to pivot to machine learning. Oh, never mind. I forgot again. So last thing we got to talk about here a little bit is progress reporting. So this is a small but mighty feature that we've updated for deep learning, where in the past, if you've used deep learning, you might see dialogues like I've got shown on the right here, where we have little red not responding while we just wait a few minutes to get an update and give you some progress information about how training is actually going. And long story short, all of our progress dialogues have been reworked so that they give you step-by-step detail about what's going on. So we went from having very few messages to now we have a lot of them. So you can see the step-by-step progress along with the epoch-based progress during training for segmentation and object detection. So a couple of these images on the right are actually animations that just show you what the progress steps look like a little bit. It's a very small feature, but it makes a really big difference as far as user experience goes. You can see all the different steps of the deep learning process. It gives you updates, and you don't think that it's frozen or just hanging. So let's see here. There we go. Third time's the charm. Well, I just skipped ahead first to make sure, but now we're going to pivot to some of the machine learning features. And the first machine learning feature that we're going to cover today is talking a little bit about normalization. So one of the things that we had introduced when we had our What's New webinar for machine learning last fall is that we have the ability to work with any number of bands and any type of data. As long as it's an image with bands, we can process it, meaning multispectral or hyperspectral. One of the things that's a little bit of an idiosyncrasy when working with hyperspectral data is that the range of values can actually exceed what you'd expect for 0 to 100% surface reflectance. And with machine learning, we always want our data to be in a state that's ready for analysis, and surface reflectance is that standard. So we had some missing cases for our logic when normalizing data, which we have resolved that. So now if you're working with hyperspectral data, you should notice an improved performance when actually processing imagery with machine learning models. There were some data sets that we had trouble with in the past, and you might get a model that's just blank because normalization wasn't quite right. So the only caveat here is that the normalization statistics, if you pre-processed your data and you know it goes between 0 and 10,000 for 0 to 100% surface reflectance, I always recommend to just use those values. So this is a fix to help make some data sets work, but if you know what the normalization values should be, then I always recommend that you use those. So small but important change here. Additionally, we've updated the models for machine learning models for random forest and extra trees. We've added a couple of additional parameters, the maximum features and custom max features, to help control the splitting and creation of the tree itself. Additionally, only for random forest, we added the out of bag score, OOB score, as a metric. So if you check the box for OOB score, the JSON file that's generated with the machine learning model will actually contain the value of OOB, which you can use in a little IDL script to adjust the number of estimators and maybe change the controls for max features to generate an out of bag error rate plot looking something like this. So if you're interested in this, feel free to send me an email and I can send you the little script that we've got that I had put together to use this as a starting point. So this is one of the ways that you might use out of bag. And with that, those are our machine learning features. So not too much there for machine learning. The focus on this release has definitely been for deep learning. We have a couple of other things that we've got lined up, which we'll be releasing later this year, probably a little bit towards the end of the summer. Good stuff for deep learning and machine learning. But before that, we have a few notable items that we want to run through, and I'm going to go through some of these very quickly because you can review the slides later. With our model changes, we've gone through and we've updated our deep learning tutorials to use the new TensorBoard to show metrics. And the first case for that is our extract multiple features tutorial with tornado damage as our use case there, which you saw some screenshots from before. We've also updated our extract one feature to use the new architecture as well. This tutorial was using the legacy model of just single class model, which, as I mentioned before, that's been removed. So we've updated our tutorials to follow and use the latest and greatest. In addition to that, we've also spent some time on our documentation for machine learning to go through, and at the bottom of this page, we add some additional information about each type of machine learning algorithm. So if you're just wanting to learn a little bit about them, to know maybe why to use one or the other, feel free to check this out. I still always recommend for supervised classification to use random forest, and if you're using unsupervised, k-means is also the one that I recommend. So this was something I had I called it a Jacqueline star rating, at least my little joke, like Michelin star for restaurants, a Jacqueline star rating for which algorithms I recommend or not, based on performance and how easy they are to use. So that's in our What's New or Introducing Machine Learning and ENVI webinar that we had last fall. But one other little change that we have here is the band names. So with the addition of a new type of pixel segmentation model and considering how many machine learning models we had, we decided to make sure that each image you process has a unique band name that tells you the model that it came from. So this way it makes it easy to keep your data organized if you're trying to compare between the two different architectures or two different machine learning models, so that the band names themselves tell you exactly what they were. So this was just like a small little feature that I kept getting confused on, and so I was really happy when we decided to implement it. Makes it a lot easier if you're running automated processing using the ENVI API in IDEO. Last thing, I think this is the last thing that we've got here, our tooltips have been added, well, taking a step back. So the latest release of ENVI, which is due to start coming out here, I think in the next few days, but the latest release of ENVI adds tooltips to all of the toolbox entries themselves. So here I've just got some screenshots showing the tooltips that we've added for the machine learning and deep learning tools as well, which if you hover over them, it gives you the name and a short little description of what it can be used for. So this kind of gives you a little bit more access to information instead of needing to go pop open the docs and read some things. So with that, I'm going to go ahead and stop presenting here. We'll get cameras on, and I'm going to turn it back over to Bill for questions and discussion.